Okay, so part 3, we're going to sort of change gears for a while here. Well, let me say where we're going before I get started. So I described at the end last time that when you have a eternal black hole, you can find a paradox if you consider region R to be a disjoint region with a piece on each side of the black hole. And in that case, an island appears that looks something like this. That comes from extremizing the generalized entropy. So let me remind you how this works. So the claim of the island formula is that the true S of R is given by min x over I of S gen I union R. And the claim is that this island appears and it gives a page curve that's consistent with unitarity. And today what we're going to do is we're going to derive that formula from the Euclidean path integral. Before we get into that, I want to start with some discussion of the Euclidean path integral in QFT. And basically what I want to do is I want to describe how we use the replica method to calculate entanglement entropy or just entropy in quantum field theory. And then we'll go to the gravity case and see how things differ and see where this island comes from. Okay, so we'll start with the Euclidean path integral in QFT. Of course, the path integral, the defining relationship of the path integral is that it calculates transition amplitudes in Lorentzian signature. This is how we usually think about the path integral. That is, if we want to calculate the transition amplitude from a sort of a position-like eigenstate with field data phi1 to an eigenstate with field data phi2, then we can calculate that by a path integral with boundary condition at t equals 0 given by phi1, boundary condition at t equals t given by phi2 of e to the I times the Lorentzian action. Now, I don't want to keep writing path integrals with exponentials and so on. So what I'm going to do in this lecture is to use a diagrammatic notation for this path integral. This notation is sort of standard. I think it's used quite a bit, although different people have different conventions for exactly how to write everything. But here's how I'm going to do it. So this is a path integral which starts with, at the bottom, with field data phi1. Then we evolve by Lorentzian time t and put the final boundary condition phi2. Okay, so this cartoon is just the cartoon picture means the integral above. Okay, so this is exactly the definition of that picture. In Euclidean signature, you can draw a similar picture. So in Euclidean signature, the evolution has no I in the exponent, but we can still calculate transition amplitudes under this non-unitary, so it's not unitary evolution, but we can still calculate the matrix elements of this operator by a path integral. In this case, it's a Euclidean path integral with boundary condition phi1 and phi2 of e to the minus the Euclidean action of phi. And this I will also represent by a picture like this. It means something a little bit different than the picture above, because this picture represents the Euclidean path integral with e to the minus Euclidean action versus the Lorentzian path integral with e to the I times Lorentzian action. So these are just, so anytime we draw one of these pictures, we have to say whether we're drawing a Euclidean picture or a Lorentzian picture, but otherwise this is just shorthand for writing all those integrals. Good. Now, the pictures that I'm writing here calculate numbers, right? This thing that we just calculated is a number. It's a matrix element of that operator, but it's very useful to think about this formally, not as a number, but as an operator. To think of the path integral itself as representing an operator. So formally, a path integral with two open cuts defines an operator. By an open cut, what I mean is we just don't specify the boundary condition. Okay, so for example, the thermal density matrix e to the minus beta h, well, this is just the path integral that I just wrote a minute ago, right, up here with Euclidean time evolution beta. Okay, so if we want to represent that operator as a path integral, we can represent this as a path integral on a strip of size beta. In this one, in this expression, I haven't filled in the boundary conditions. I'm not putting a phi1 at the bottom or the top. So this is what I mean by two open cuts. These are places where you haven't specified the boundary condition. And it's useful to think of it this way. Formally, it's clear that this is an operator, because what is an operator? An operator is something that takes two sets of field data and turns it into a number. So if you hand me a phi1 and phi, so in this case, if you hand me a phi1 and phi2, I give you a number. So that means that this is representing an operator. This is just equivalent to the statement above that tells you how to calculate the matrix elements of rho. Is that clear? Any questions so far? Okay, so another statement which I'll sort of gloss over, but it's also true that a path integral with one cut defines a quantum state. Because what is a quantum state? A quantum state is a linear functional on field data. And that's what a path integral with one cut is. You give me one set of field data and I give you a number. Okay. We can use this to calculate the thermal partition function at temperature beta. So let's do that calculation. The thermal partition function is trace of e to the minus beta h, which is the sum over states of phi e to the minus beta h phi, which we can represent as a path integral as integral d phi 1 of x of a path integral oops, on a strip of size beta, where we put phi1 at both the top and bottom of the strip. So I've just converted that matrix element in the second line to a picture, a path integral picture in the third line. Remember, this is just shorthand for the path integral that I don't want to keep writing. But this expression, what is this? This is a strip of size beta with a boundary condition that says the top is equal to the bottom, but can be anything, because we integrate over phi1. Well, a strip where the top is the same as the bottom, that's the same as a cylinder. Okay, so this is the same as a cylinder of circumference beta. Again, this last expression is a picture that just means do the Euclidean path integral on the manifold pictured here. If you think back to our discussion of Hawking radiation, I said that thermal field theories are periodic in imaginary time. This is another way of seeing why thermal field theory is periodic in imaginary time. For example, if we were to calculate the correlation function x tau 1 y tau 2 at temperature beta, then we could go through exactly the same argument that we just used to derive the cylinder picture, and we'd get the same answer, but with some operators inserted in the path integral. So this is given by a path integral where you have some operators inserted in the path integral. So this picture just means do the path integral with these additional operators under the integrand. Well, from this way of writing it, it's totally obvious that this is periodic in imaginary time. Because if we move one of those operators all the way around the circle, then it's just going to get back to where it started. So this is another way of seeing this property of thermal correlation functions. Good. So we've reviewed how to represent an operator and the thermal density operator as a path integral. And now I want to discuss a subregion. That is, I want to discuss the path integral representation for the density matrix of a subregion, rho A. Let's start in some state psi. The state psi, I'm going to take the state psi to be created by an operator inserted in the Euclidean lower half plane. In terms of operator language, I'm defining a state by inserting an operator, by hitting the vacuum with an operator. In path integral language, this state looks like this, where we go down the distance tau naught, and let's see, how do I want to draw this? So this is a path integral on half of R2. It's a path integral on the Euclidean half plane. And this is a way of preparing the state psi. This defines a quantum state because it's a path integral with one open cut. In other words, what's really meant by this picture is that you can use it to calculate overlaps phi1 with psi by inserting the field data on the cut. This field data phi1 is just stuck onto the cut, and then you do the path integral. Okay, so this is a way of it's basically true that in any quantum field theory, it's basically true that any quantum state can be represented this way. There are caveats to that statement. The more careful statement is that by inserting operators in the lower half plane at various points, you can insert not just one, but many operators, that if you insert many operators in the lower half plane, you can then, the set of states that you can produce that way is dense in the Hilbert space. So you can get an arbitrarily good approximation to any state in the Hilbert space. That's just an aside. Now let's talk about the operator rho that's the density matrix in this state. Well, the density matrix in a pure state is psi psi. So if I'm to write this as a path integral, I'm going to write it this way. Okay, so the one of these, it doesn't matter which one of these is the bra and the other one is the ket, and I've drawn them as the upper and lower half plane. So you can think of the density matrix in the state psi as being a path integral on the full plane, but with a cut on the real line. And in that cut, we're supposed to supply, if we want to turn this into a number, say we want to calculate the matrix elements of rho, like phi2 rho phi1 is a number that we would calculate by doing this same path integral, but supplying field data on the cuts. Phi1 on one of the cuts and phi2 on the other cut. So that gives us a number. Is that clear? Are there any questions?
Sorry, it's in the closed cut or the infinity sign that you have. Does that mean the vast state?
So you're cutting out a bit. I think based on half the words I heard, I think maybe you're asking what this infinity means. Is that right?
Yeah, yeah.
Yeah, so that means that we just do the path integral on the infinite half plane. And the only boundary condition we have to, so when you do that, you don't really have to impose boundary conditions at infinity. All you have to impose is regularity at infinity. So that represents the integral on the half plane with regularity at infinity. If I did not put in the operator O, this would prepare the ground state. There's a simple argument for that, which is that when you evolve by e to the minus infinity h on any state, this projects onto the vacuum, that is onto the state of lowest energy, because of the exponent being suppressing all of the other states.
Okay.
Are there other questions? Okay. Go ahead and interrupt if there are questions. So I'm trying to go through the QFT part sort of quick so we can get to the gravity part, but it has to make sense or we're going to get really lost. Okay, so please do stop me for questions. So this is okay, so where are we so far? We have the path integral representation of the operator rho. Now what we want to do is define the operator rho A. That is, we take, well, in this case, I'm drawing these, by the way, I'm drawing these as if we're doing a two-dimensional or 1+1 dimensional field theory. All the ideas generalize to higher dimensions. You just have to put more dimensions in the diagrams, but it's easier to draw the pictures in 2D. I'm going to keep using the two-dimensional language, although the arguments apply to higher dimensions. So in 2D, space is a line. And that means that when we talk about a subregion, subregion is an interval of the line, or it could be multiple intervals, disjoint intervals. I'll just talk about the single interval for now. And we want to define rho A, which is the trace over A complement of rho. That's the definition of the reduced density matrix on region A. So we're just going to follow our usual bag of tricks here to translate this into a path integral picture. So what is the trace over A complement? That's a path integral over fields that's a path integral over fields defined on A complement of the density matrix. So let's put in our picture for the density matrix. I better make this bigger so we can get enough detail on here. Okay, so our density matrix here's the ket, the bra, and here's the other one. Now that was the density matrix as an operator, but now we're calculating matrix elements that are sandwiched against the field data on A complement. So let me separate this into region A and A complement. And we're doing the trace over A complement. Now remember what happened in the thermal partition function. In the thermal partition function, we started with the operator was a strip, but when we did the trace glued the ends of the strip together and turned it into a cylinder. So tracing, or in general matrix multiplication, glues Euclidean path integrals together. So in this case, the field data on A complement is specified here and here and here and here, but we're not specifying field data on region A, because the thing we're trying to calculate is an operator on region A, and we're supposed to leave those cuts open so that it remains an operator. Well, if you do a path integral like this, and you integrate over all possible field data on A complement, that's exactly the same as just gluing them together. So this is the following path integral. What's meant by this picture is that there's two open cuts. That is the top and bottom of region A in the Euclidean sense. And that means that this picture that I'm drawing is a functional of two sets of field data on region A. In other words, this picture that I'm drawing is an operator on the Hilbert space associated to region A. So this is our answer for the path integral representation of the density matrix rho A. Again, the cuts on A complement have gone away due to the partial trace. We still have cuts, we still have open cuts on the top and bottom of that red line, and that's because this is an operator. If you want to turn it into a number, you have to supply field data on the top and bottom of the cut. So this picture is...
Sorry to interrupt. I had a question. So you had this previous operator insertions in the above picture, which are like O in the above and below both strips.
Ah,
So
the
in
O's,
the
yes.
blue picture, how are those?
Good.
Yeah.
Sorry, I just forgot to draw the O. Thank you. There.
So when you make this integrals over the phi A complement fields, does some part of the O also get integrated? The part which had support on, say, the A complement region?
No. Well, no, that doesn't get integrated. That's just that's an operator that's inserted somewhere off the real line, so it's not going to get integrated over. So the meaning of this final expression is that when you do the path integral, so when you convert this to a number by supplying field data and doing the path integral, you should do that path integral with an O of with two O's in the integrand at the points in the picture.
Okay, thanks.
Are there other questions? This picture is crucial, so please do ask if it's not clear. I can explain it again. Okay, so what we're going to do now is calculate the entanglement entropy in a 2D CFT by the replica method. This is a calculation of this is a calculation of Cardy and Calabrese. They did it exactly the way that I'm going to do it. So you should think of this as a warm-up calculation for the case of calculating entropy in quantum gravity. Of course, here we're just doing conformal field theory. So there's going to be some extra ingredients when we get to gravity. So so I have my Slack on, and I can see people asking questions about the lecture. But please just jump in, and maybe those are people on YouTube, so maybe they're unable to ask questions. If anybody knows what the question is, I can try to answer it. I'm not going to try to go into Slack and read it in real time, but
there were a few questions on Slack, but there were quite a few, and there was also some discussion going on Slack, so that's why I didn't forward them to you yet.
Okay, if anybody wants to distill a question and ask, go ahead. But otherwise, I'll just keep going. I'm going to sign out of Slack so that I stop getting beeps. One sec. Okay. Okay, so we're going to do this calculation of Cardy and Calabrese. So what is the idea? The idea is that we want to calculate S of rho A, which is minus the trace of rho A. I'm going to put a hat on this density matrix. The reason I'm putting a hat is because in this discussion, it's convenient to use normalized and unnormalized density matrices. So the expression for the von Neumann entropy assumes that the density matrix is normalized. So rho A hat is rho A over its trace, normalized to have unit trace. Then the idea of the replica method is, well, it's hard to calculate a log of an operator. The motivation for the replica method is it's hard to calculate the log of an operator. There is no path integral that you can write down that calculates the log of an operator. There is, however, a path integral you can write down that calculates a power of an operator. So the idea of the replica method is to calculate the replica, what are called the replica partition functions, or well, if you take a log of this, it's called a Renyi entropy. So you calculate the replica partition functions Zn. Those can be calculated by a path integral in many cases. So this gives you a path integral to do. And then the idea is to calculate the von Neumann entropy, S of rho A hat, by analytically continuing to n near 1. The von Neumann entropy is given by by something that looks very much like the usual thermodynamic formula for entropy. 1 minus ndn log Zn evaluated at n equals 1. You can easily just plug in the definitions here and check that this does indeed give minus trace of rho hat log rho hat. Okay, so this is the idea of the replica method. And the motivation is to be able to do it by path integrals. The replica partition function is the following path integral. Well, let's make a new page here. Okay, so the replica partition function which is trace of rho A to the n, is computed by the following path integral. So Zn so we're just going to take the path integral for the density matrix and do matrix multiplication on it. So what does matrix multiplication mean? Well, let's start by writing the first well, I should have mentioned that I'm going to be taking the state. I'm going to be working in the vacuum state. So that is, we take the initial density matrix to be 0, 0. Now we don't have to worry about these operator insertions. We just take away the operator insertions. Okay, so what is the path integral? First, let's just draw n copies of rho A. There's 2, ... up to n. So those are our n copies of rho A. Now we want to multiply them together. So how do you multiply two matrices together? You give them the same index and then sum over it. Well, in field theory, that means to glue. So if we want to multiply, say we want to multiply the top operator, the first operator by the second operator, well, that means that we should put the same field data on the bottom cut, or sorry, well, we can go either way. Let's say we put the same field operator on the top of the first cut, this green line here. We put the same field data there and on the bottom of the second cut. So that is, we identify these two cuts. We put the field data there, and then we sum over it to do the matrix multiplication. But just as we discussed in the thermal trace, this just has the effect of gluing the manifolds together. Similarly, now we want to multiply, say, the second operator by the third one. Well, let's pretend there are just three, so I don't have to worry about the ... dots. Then we should glue the top of this cut to bottom of this cut. And finally, when we get to the end and have to do the trace, we should glue the top of the last cut to the bottom of the cut on the very first sheet. So this is an n-sheeted surface. So we're doing a path integral on an n-sheeted surface, which is defined by doing the gluing in the way specified in this diagram. Okay, so we glue the same colored things together when we do this path integral. Does that make sense?
So on the Slack, there is someone asking if you could elaborate a bit more on why it's called the Replica partition function and what is the motivation for it?
Yeah, so the idea is if we go back here, so the idea is we're trying to calculate the log. We're trying to calculate this thing. We're trying to calculate this thing. It has a log in it. Logs are hard. So instead of calculating that, we're going to replicate, we're going to make multiple copies, fake multiple copies of our system. That's replicating. So we have many replicas of the physical system. So we take n replicas. Then we calculate this thing, which is called the replica partition function, just because it's the partition function of n replicas. And once we've calculated that, we're going to try to analytically continue in n and use that analytic continuation as n goes to 1 to calculate the log. So we're thinking of log as being a power. So log, of course, is related to power to an object to the 1 plus epsilon, where epsilon is small. So that's why the n near 1 limit gives the log. Are there other questions?
No other questions.
Anyone who's live have questions? Okay. So this is a path integral on what's called the replica manifold, m sub n, which is a branched cover of the plane consisting of n sheets of the complex plane glued together along the cuts for region A. The cuts along region A. Okay. I'm trying to decide whether to actually do the calculation. Let me just sketch so the next step is to calculate this. You need to calculate the partition function of a CFT on this manifold. I think I'm going to skip this calculation, the details of this calculation, but it can be done in one page, and the full calculation is done in the lecture notes that'll be posted afterward. Let me just sketch how this goes. The first step is to define a global coordinate on the so each of these planes is, say, a z plane, the complex plane z, but there's n different copies of z. So the way to do this calculation is to introduce a global coordinate w, which covers the entire replica manifold. The way this works is as follows. You take a ratio of these guys. Z1 and Z2 are the endpoints of region A. And this coordinate W is a global coordinate on the replica manifold. then you can use conformal transformations. So you know that on the W plane, the partition function would just be trivial. So then you can use conformal transformations and use the conformal anomaly to calculate the partition function on the original manifold. So that is Z on just the W plane with trivial metric dw bar would be 1. But we're not on, we don't have metric dw bar. We have metric ds squared is equal to zz dz bar. And so you can write that as a conformal factor times dw bar, and then use the conformal anomaly to calculate the contribution of this conformal factor to the partition function. So I'm just going to skip a few steps and tell you that that's given by Zn is Z1 minus Z2 to the minus 2 delta n, where delta n is C over 12 times n minus 1 over n. C is the central charge that appears in front of the conformal anomaly. And this expression, you'll notice, is identical to the 2-point function of a primary operator. It's just a power law. So the answer is a power law. And so that corresponds to the 2-point function of a primary operator. There's sort of this defines for us a primary operator called a twist operator. The twist operator sounds fancy, but it just means this. It just means this replica. It just means this calculation. So the replica calculation defines what's meant by defines the correlators of the twist operator. So this is a twist operator 2-point function. Now, a priori, this calculation made sense only at integer n. There's a question in the chat. What does it say?
Question on the chat says, can you expand on why the cuts need to be identified between the replica copies?
Sure. So why are the cuts identified? We're calculating trace of rho A to the n. So this is trace of rho A, rho A, rho A dot dot dot. And the way to think about this is that, well, we want to multiply, when you want to multiply two operators, we can insert in here the identity in the form sum over phi of phi phi. So we can insert that resolution of the identity between every one of these row operators. And then we're going to get something like a path integral d phi 1, d phi 2, d phi 3 dot 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 of phi 1 rho A, phi 2 rho A, phi 3, okay, etc. With the final thing being a phi 1 again. So let's look at the first two here. And let's focus on phi 2. Okay, so as a path integral expression, this phi 2 is the field data being supplied to the first operator. this phi2, so this is what I was representing as, I guess we're talking about the green parts. So this phi2, this is the top of the first cut. This is the field data on the top of the first cut. This phi2 is the field data on the bottom of the second cut. And so on and so on. So each time we do one of these multiplications, multiplying two operators really just means gluing the manifolds at the cut. Is that clear? Other questions? Okay, there's a question, is it possible to calculate any other correlators of these twist operators using the replica technique? Yes, that's true essentially by definition of the twist operator. The twist operator is more or less by definition given by replica calculations like this one. So for example, if we wanted to calculate, let's call the twist operator sigma. If we wanted to calculate a 4-point function of sigma, then we would have 2 cuts instead of 1. If we wanted to insert some other operators into that correlation function, then we could insert some additional operators into these path integrals and calculate that as well. Okay, where was I? Let's see. Okay, so we got the partition function. Now we're going to calculate the entropy. The entropy is S is 1 minus n dn log Zn at n equals 1, which is, you just take this derivative, this will give you C/3 log L plus a constant, which is undetermined by this method. And that's the right answer. So L here is the length of region A, generally the proper length of region A. Okay, if you take a look at the notes afterward, it's a very good exercise to work through this calculation. I didn't do all the steps in the lecture, but I give you enough information in the notes that you can do every step and make sure that you get this same answer. There's a question in the chat, do odd correlation functions of twist operators signify anything physical? And the answer is that they're 0. The odd numbers of twist operators, so twist operators have associated to them a charge, which you can think of as whether it's the left or the right of the interval. So the one on the left has a minus, the one on the right has a plus. And if the twist operators, if the correlation function has net charge, it doesn't add up to 0, then the correlator will just vanish. Okay, so that's a good exercise. I recommend everyone work through that and reproduce that C/3 log L. There's a couple important comments here. Well, there's something I want to emphasize because this is going to be different when we get to gravity. So what I want you to note is that in this calculation, the metric on the replica manifold is dz dz bar on each sheet. So really there's n different copies of the z variable because there's n copies of the complex plane. and the metric is flat in each z variable. The fact that the metric is flat means the manifold is singular. Mn is a singular manifold. So why is that? Near a twist point, near a twist operator, that is an end of region A, you have to go around it. So let me go back to the picture. Okay. Let's look at this point here. We can ask, what do you have to do to get back where you started? So say I start here, and then I want to go counterclockwise around the circle. How many times do I have to go? How far do I have to go before I get back where I started? Well, here I am walking around let me erase the circle, and then I can do this in real time. Okay, I start here. I'm going to walk around the circle. I'm walking around the circle. I'm walking around the circle. I get to here, and I find, oh, I'm actually going to land down here on sheet 3 because I have to follow the blue line. Now I'm walking around the circle again. I keep walking. I get to the yellow line, and I find myself here on sheet 2. Now I just continue walking around the circle till I get to the green. When I get to the green, then I'm back here where I started. Okay, so if I sit near one of these points and I want to go around a small circle, I have to go around n times to get back where I started. So what does that mean? That means that in the vicinity of one of these endpoints, the twist defect, z minus z1, the coordinate z minus z1 is identified, but it's identified with an angle which is 2 pi n. So this is equal to z minus z1 e to the 2 pi I n. The angular coordinate around that point has the wrong periodicity. So the angular coordinate theta around that point is equal to theta plus 2 pi n. And this is a conical excess. The manifold is not smooth. In particular, the replica manifold, when you do these calculations in quantum field theory, the replica manifold is not a smooth manifold. It's singular. It does not satisfy the Einstein equations at the defect. Okay, I think we're going to stop here for the first part and do questions and then a quick break.
All right, it didn't seem like there were many questions left unanswered on the Slack. There was one question about how to think about the replica manifold and whether to think about it like flat space, but I think you basically just answered that.
Okay, so if people want to take a quick break and think for 5 minutes about other questions, then we can see if there are questions when we get back and then move on to gravity.